We were given a task by British Cycling, Jacobs and Body Rocket to develop techniques to measure the load applied to a bike while cycling. We were encouraged to explore novel ideas rather than just use techniques that had previously been used. Studies into common injuries caused by cycling have identified that knee pain and lower back pain are the most common, with patellofemoral pain being identified by elite cyclists as the main type of injury that impacts their performance. During research, I was curious how seat position affected these compressive forces, but how do we estimate them? Rather than measure the forces directly within the knee, we can use a method called inverse dynamics. To complete an inverse dynamics calculation of the lower leg, we require two streams of data. One, the external forces applied to the leg, which my colleagues were attempting to measure. And secondly, the angles, position, acceleration of the lower body segments, also known as kinematics. To gain the kinematic data, previous research tends to use image processing or high-speed video recording equipment. Rather than use video recording, I decided to create a 2D model of a cyclist's leg for a full revolution of the pedal in MATLAB. I would attempt to simulate the kinematic data required to estimate the forces in the knee. Rather than use a real rider and a real bike and hours of video post-processing, a simulation instead takes a few seconds. Furthermore, the variables can be updated and changed easily. The system has an infinite number of positions, so we require two boundary conditions. One is the hip being located at the origin, and the second was taken as the ankle angle. Originally, I used 90 degrees for the ankle angle, but as an improvement, I used published data to make the ankle flex, making the model more realistic, as you can see on the right-hand side. Until I received some data from my colleagues, I was required to estimate the forces applied to the pedal depending on the crank angle, for both the normal and the anterior-posterior forces. This I did by completing a curve fitting to previously published experimental data. So shown in red are the reaction forces of the pedal applied to the foot, which we obtained from the previous two graphs. To estimate the patellofemoral compressive forces, we use a free body diagram, such as the one on the left, until we obtain an equation for the resultant moment in the knee. So to summarize, we run a two-dimensional simulation of a cyclist on a bicycle in MATLAB and saw the resulting kinematics. We then, for a given cadence, can calculate the associated linear and angular accelerations of the shank and the foot. And with the experimental force data and the simulated kinematics, we can then complete the inverse dynamic calculations from the foot into the ankle and then into the knee for each point in the revolution. We can then run a simulation and then estimate the forces in the knee during the whole revolution. So in this case, we use a standard person for a standard bike with a standard seat position with a cadence of 90 RPM. Here is a graph of our simulated patellofemoral compressive forces compared to previous work using image processing. Some of the variance is expected due to different heights and masses of the riders, but the results seem to indicate that the model could be used to estimate forces in the knee. So we then completed the simulation again a further 10,000 times using a randomized seat position within a range of 20 centimeters by 20 centimeters, as you can see on that image there. The maximum compressive patellofemoral forces were then stored for each seat position. The image on the left showed the results, with each dot representing a simulation, and the color contour is related to the maximum compressive force. The results showed that the maximum force increases as the seat is lowered as well as moved backwards. This agrees with previously published work, so it could then be recommended to move the seat forward and upwards during rehabilitation to reduce the compressive forces in the knee. And then as the cyclist continues recovery, the seat can be moved backwards and downwards. As my colleagues had now recorded force data on the pedal, I updated my model and then updated it to reflect the cyclist's mass and height, and the simulation was completed again. The results showed a similar compressive knee force as the previous inverse dynamics work, though the forces were slightly higher in the second half of the revolution. One possible reason for this is the bicycle we used did not use cleats, and the previous experimental work did. My recommendations for further work would be that the current model uses previous ankle flex data to simulate the position of the leg. In reality, the ankle angle would change when the seat position changes. So using this function on the screen here would create a more accurate model. Secondly, the current model only uses 2 dimensions to estimate the forces, so a further model could be created with 3 dimensions instead. If a further model was to be developed, it would be interesting to have a look at the power generated, depending on seat position, just as a further comparison. So, in summary, we managed to estimate the forces in the knee using recorded reaction force data from the pedal. Rather than use traditional image processing techniques to provide the kinematic data, we instead used a simulated 2D model in MATLAB. We then used the generated data to complete the inverse dynamics to estimate the force in the knee. Thank you for listening, and if you have any questions, please feel free to contact me.